The purpose of this project is to learn new skills and concepts by making a functioning autonomous drivetrain prototype. We wanted our drivetrain to be able to go forward until it sensed a wall, turned, and then moved forward again. The resources we have used so far are an Arduino Uno, 4 wheels, 4 shafts, 2 motors, 2 motor controllers, 8 bearings, a breadboard, a battery, so 2 batteries, 3 printed parts, plywood board, and an assortment of wires, washers, screws, etc.
We began the initial design using the computer-aided design software Onshape. The design consisted of one plywood plate where all the components were mounted on. On top of the board, we would mount 2 motor controllers, an Arduino Uno microcontroller, a breadboard, and our ultrasonic sensors. On the bottom side, we designed mounts for the motors and wheel axle setup. In order to engage the output shaft of the motor to the axle, we designed a 3D printed coupler for the bolts to go into. Initially, we wanted to create a 4-wheel drive, so we modeled and 3D printed pulleys and tensioners to increase the friction of the pulley system. However, we eventually decided to pursue a different design for the pulley system.
We started the build process by preparing the necessary components. This means that we 3D printed our designs, cut and drilled aluminum shaft, and cut and drilled some wood. We also acquired some bearings and basic hardware like the nuts and bolts. Once the basic components were assembled, we tried getting the 4-wheel drive to work, which used 3D printed pulleys and polycord. We first tried melting the cord together in order to create one full loop. That didn't work, and we tried using super glue. That also didn't work, and what ended up working was using just zip ties and making sure the rope was sufficiently tensioned while we zip tied it. We also had a problem with friction of the cord to the pulley, but also tension of the cord, and we tried using zip ties all over the cord to act as teeth, and we designed pulleys that also had teeth within them so that it could grip a little bit better. And to solve the tensioning problem, we designed these little mounts to bolt shafts at certain distances so that we could increase or decrease tension however we saw fit. We ultimately ditched that 4-wheel drive to simply use 2 powered wheels in the back. As mentioned before, we created and designed this little 3D printed coupler to engage the motor with the axle, and we designed some little holes so that nuts can go in them and bolts would have a better grip to grip onto the shaft. With this, our wheels were now engaged to the motor shaft. We then moved on to testing out the sensor. This was pretty much a breeze because one of our members had previous experience with working with these sensors and Arduino, so we figured out how to wire it to the Arduino, and we just used some pre-existing code to print some distances that the ultrasonic sensor was detecting through trig and echo logic. Once that was done, we worked on wiring up the rest of the robot. We went through a couple of failed components for speed controllers for the motors, but after a couple of attempts, we got some working components. Although the wiring looks rough, it did work, and it was a good start for our project. Now it was time to run code to actually make the robot move. After much trial and error, we finally experienced the moment that we set the robot on the ground and saw it move a little. We then coded the motors to stop rotating once a sensor was triggered, and this code was briefly tested on the robot while on the ground until we started experiencing some more problems. The fundamental problem that we were experiencing was that the motors we had got were too low in torque, and on top of that, we had some mechanical issues with alignment in the axle setup, which didn't prefer the low torque situation. One potential solution of this is to have a gear reduction from the motor to the axle, which would optimize for more torque. Another solution that we can implement is having a body that weighs less, because we are actually using a big piece of plywood, which is pretty heavy. Another big problem that we had was that one of the motors was not spinning as fast as the other one. This we later found out was because of some smoking that we experienced of the motor when we had initially tested the motors when we got them. At this point, we fixed up all the wiring to look nicer and more workable, but we are still experiencing problems with the output torque of the motor and also some code issues from the sensors. To conclude, We all agreed that we had learned a lot from this little drive base, and we will take what we have learned from this project to more practical projects. Nevertheless, we still see potential in this drive base, so we plan on returning to this project and implementing some solutions, while also making the project more practical. Thank you for watching, and stay tuned for more content by DET on YouTube, Instagram, and TikTok.